Dinesh Sharma here. Welcome to Art. Today we guys are going to start our new topic, which is mathematics. We are going to be starting with the vectors, and we are going to continue with more and more topics thereafter. So we are today going to start with vectors. We will cover vectors in the next 2 videos, and afterwards we are going to talk about different things. Today we guys are going to start with the vectors. Now let's start with the vectors. Starting with the vectors. Now let us first define what is a vector. Before defining a vector, we need to define what is a quantity. Quantity can be divided into two methods. First one is scalar, and another one is vector. So we have quantity can be defined as a vector and as a scalar. The quantity can be defined into two ways. First one is vector and second one is scalar. So there are two ways to define quantity. Now what is a quantity? Quantity is anything we can measure. For example, mass, velocity, distance, anything you imagine that can be measured in a quantity. And we can measure all the things in two terms. First one is vector and second one is scalar. Now let's see what is the difference between scalar and vector and what are they. Starting on with the vector, let's start with the scalar. Scalars are basically those quantities which have only magnitude. So quantities which have only magnitude are called scalars. For example, mass has no direction associated with it, hence scale, which has only magnitude as well, or nothing else, does not associate with any direction. That kind of quantities are called scalars. For example, mass is basically a scalar quantity because it has no direction. You don't say it is 40 kg in this direction, 50 kg in this direction. Mass of a person is weird, and it is scalar. Hence mass is one of them. And the other quantity that we talk about is length. Now let's say we are measuring length of cable or of a phone. You measure it from up way down or down way up, it will still come out to this. Let's say if there is a 40 meter. Either you are going to measure in this way, direction or in this direction, it's going to be 40 meters. So length is one of them. Which direction does not, in which direction you are measuring, the result is in this way. That kind of thing is called. Now let's move on to the vector. So vectors are those quantities which have a direction. Quantities with magnitude as well as direction. These kind of things are called vectors. Now, examples of vectors are simply velocity. As you know, velocity is the directional speed. In which direction you are moving and what speed are you moving with, that tells you the velocity. It is in direction, right? So there is some direction associated with it, that's how it is. For example, let's say particle is moving, and you are standing here by, and trying to calculate the velocity of the particle. The speed of the particle throughout this will might be constant with the velocity. We are going to measure the velocity in this direction. This direction velocity is x. The particle turns this way and its direction has changed in this direction, which is perpendicular to the radius. This is nothing else but the nature of the circle and how it is the direction. So, as the direction or the magnitude of the particle is changing, these are the examples of the vector quantity in which direction also not just the change in magnitude means that your magnitude of the quantity, but also the direction. The direction of the particle that means. So, first one is velocity. Afterward velocity, there are something else called displacement. Length was a scalar quantity with displacement. Displacement tells us how far our particle has displaced from this point. Let's say our particle was here, at some point the particle was here, it has displaced to this much distance. Let's say particle might have displaced here. Then these two are not same thing. As they have moved in different directions, the displacement in both the cases are different, as our quantity depends on the direction. The quantity depends on the direction. So that's how the vectors are defined. So these are two examples of vectors: velocity, displacement, and the examples of the scalar are really good. That quantity which does not associate with the direction are called scalars. These kind of quantities are called. And there are some other things like you can associate with them. Acceleration also have direction associated with it. Electric and magnetic field, like momentum. You can associate any much quantities you want. These are two examples of vectors. Many students are confused with two more quantities that seems like a vector but not a vector. That actually changes the definition of vector in this vector. First quantity is current, and second one is time. Now, current has a direction associated with it, and the time as well has a direction. Now, current always moves from positive terminal to negative terminal. Right? Current always moves from positive terminal to negative terminal. Some of you might be thinking how I write positive terminal to negative terminal. Electron moves from negative to positive terminal, but here I am talking about the conventional current, which usually travels from positive terminal to the negative. I am talking about the conventional current. And the times always move forward. Time always moves forward. Time never moves in the backward direction. So these things have a direction associated with it. But still these things are not a vector quantity. Similar to that of time. So time always moves in the forward direction and the current also moves in the forward direction. Let's say I have a wire here. Let's say I have a wire here. Suppose I1 current is going through them and the I2 current is going through them. And this is the wire. By connecting these wires, this is the result. The current through this wire is basically I1 plus I2. If I am going to change the angle between these two, let's say there is an angle theta between these two. The quantity I is equals to I1 plus I2 does not change that. I1 plus I2 does not change that. It will remain similar as it was previously. So that's how the currents are not vector quantities, they are scalar. Currents are not vector quantities, they are scalar quantities because it does not follow the rule of vector addition. So current doesn't follow law of vector addition. As they don't follow the law of vector addition, it simply means that they are not vector addition. If they are vector, they should necessarily follow the law of vector. If they don't follow vector addition, they are not vector. So current is nothing else but a pseudo scalar. This is the additional information I am giving you. It's not usually given in many books. Current is a pseudo scalar. which is a scalar quantity but changes as the direction. For example, current moving in this direction will be I, and the current moving in this direction will be C. You might already know about this thing. So these things are nothing else but the pseudo-scalar. Current is a pseudo-scalar. While calculating magnetic field, you might already remember that we take I cross with R. We are treating here it as a vector, and it behaves like one as well. It behaves like one as well in the case of magnetic field. But it's not a vector, it's a pseudo-scalar. Same goes for the time as well. So for the time, it is also pseudo-scalar. Now let's move on to furthermore the multiplication and the addition of the vector. First, let's talk about the scalar multiplication. How do scalar multiply with vector? Scalar multiplication here, I mean scalar multiplying with vector. Because I'm talking about vector here, so when I'm going to state vector multiplication, vector multiplying with vector, and now I'm talking about the scalar multiplication. So how do scalar multiply with vector? So let's say our A multiplies with the vector, simply multiplies. There is no way. Now there are some properties associated with it. For example, you might already. Now the solution to this particular will be simply A plus A. So it follows this property, which we call this property. Again, recalling this property is called distributive. So your scalar multiplication is distributive in the name. Now let's talk about another property that is associative. Now let's say A is multiplying to a vector which is already multiplication of scalar and a vector. Now I can simply state in this manner A multiplied with B, then multiplying with A, similar even to B multiplying with A. So it follows this kind of properties. That's how it is associative as well. Now again, moving on to the commutative part of it. A multiplied with a vector A or vector A multiplied with A, similar. That's how it follows. So these are the properties. And the resultant is always going to be a vector. Resultant of a vector addition, vector and a scalar multiplication is always going to be a vector. If you are going to multiply a scalar with a vector, what is going to come is the vector. It will always result in vector. So these are few properties of vector multiplication. Now let's talk about vector addition. Now here I am adding vector with a vector. Previously we have multiplied scalar with a vector, but we cannot add a scalar with a vector. Only vector can add with another vector. We cannot add with another scalar. So this is first part. Vector can only be added with a vector. The vector can only be added to the vector. It cannot be added with any scalar. And the second property is resultant is always going to be a vector. Resultant is always going to be a vector, which in this case we address as the closure property. In this case we address as a closure property. Okay. Next point is commutative. Now vector addition is also commutative. We simply address it as in this manner. Let's say A vector adds with B vector is similar to B vector it adds with B vector. So it follows the commutative law as well. Moving on to another part, which is associative. Now associative kind of property is that A vector is added to B vector, then added to C vector, is similar to the B and C vector are added together and then added to B vector. These two are nothing else but the similar thing. So it does not matter in which sequence you are adding them, you are going to get the same result. This kind of property is called associative property. Fifth one is distributive. Now it is not distributive in the vector sense, but it is distributive from the scalar multiplication point of view. So M is multiplying with A and B, it is simply A vector. If some scalar is multiplying with the vector addition, it can also be treated as a multiplying with the vectors then adding vector. So adding vector and then multiplying with the scalar quantity is similar to scalar into vector plus scalar into vector and then adding them. It is similar, highly similar to this thing. So we can state in this thing. Both these are nothing else but the same. So that the first one was the scalar multiplication, second one was the vector addition, and now we are going to talk about a very prominent scenario, which is vector multiplication. Now vector multiplication is a very important part of your course. First kind of vector multiplication is the scalar multiplication, or you can call it dot product. Dot product or scalar product. Next one is cross product or vector product. Now when two vectors multiply, they can result in a scalar as well and they can result in a vector as well. Now it depends upon what kind of multiplication they are following. It depends upon this thing, that what kind of vector they will result in. Now let's talk about the first one, which is dot product. First one is the dot product. Now dot product is basically represented in this manner. Basically a dot product is represented in this manner. It can be stated as a dot product of A vector. It can be written in this manner, A vector dot B. Now it can also be stated in this manner, magnitude of A, magnitude of B of, that is, let's say we have two vectors here. This is a vector B, this is a vector. Now the dot product of these two vectors, as they have some different directions as well. As the vectors have different directions associated with them, we cannot multiply with them simply. In the case of scalar, they don't associated with any direction at all. That's why we used to multiply them in a simple way. So in this case, what we have to do, we have to change, we have to take both the vectors into the same direction. And what we do here is simply take the projection of B in the direction of the A. That is, A vector is here. We are going to multiply with the projection of the B vector, which is nothing else but the B vector into cos theta. B vector into cos theta. This is B vector into cos theta. Similar manner, the projection along this direction would be B vector into sin theta. this is what we are doing. We are simply taking the magnitude of these two and taking the cos beta times of this particular vector so that both will get into the same direction, and multiplying them will result me into the dot product, which is nothing else but represented by this. So that's how the dot product of a particular vector is defined. A dot b is equal to a magnitude into b magnitude into cos of beta. Now this beta is nothing else but the direction, the angle phi between the two vectors, so that we can get one of them in the same direction as the other, so that we can multiply. So that's how the dot product is calculated, and it will always result into a scalar quantity. Its resultant will always be a scalar quantity. The resultant of this particular, this is very important, this resultant of this particular multiplication will always be a scalar quantity. So this is the one part. Now usually this a dot b can be written as, if the a is written as, the a vector is written as ax I cap plus ay j cap plus az k cap, and the b vector can be written as bx I cap plus by j cap plus bz k cap, then this can be represented as ax bx plus ay by plus az dz. So we are simply multiplying each coefficient with another coefficient. This is the vector representation. This is the representation of a vector. Let me introduce to it as well. This is another form of vector representation. Usually a vector is represented in this manner, where the I cap, j cap, and the k cap is the unit vector. We are going to do these things afterwards when we are going to define the position vector, but I am literally associating with this vector notation. So that's how the dot product is. We are going to do this representation afterwards when we are going to define about the position. So that's how the dot product is defined. So now let's talk about the properties of the vector, properties of the scalar product. Now the first property of the scalar product is, if I cap I cap with I cap, it will going to result me into 1. Why is that so? We have taken a vector dot b vector, which results me a vector magnitude b vector magnitude into cos of theta, right? Now what if theta is 90 degree? Theta is 90 degree, that is a vector is perpendicular to b vector, right? A vector is perpendicular to b vector. In that case scenario, cos theta will be 0. Cos theta will be 0. So in that case, a vector dot b vector is equal to 0. This is the first scenario I'm talking about. The next scenario is when a vector dot b vector is equal to a vector b vector cos of theta. But here theta is 0 degree, that is a vector is parallel to b. In that case, cos theta will simply be 1, and a vector dot b vector will simply be magnitude of will be simply the multiplication of the magnitude. Now these are unit vectors. I cap and I cap are unit vectors. Now unit vectors are those vectors which have unit magnitude. So its magnitude is 1. That's how their dot product is 1. Similar goes for the j cap dot j cap, 1 as well. K cap dot k cap, which is also 1 as well. Now let's talk about I cap dot j cap. Now these two things are perpendicular to each other. I have proven this scenario as well, where the a vector dot b vector is 0. This is also 0. I cap dot k cap is also 0. Similar going j cap dot k cap is also 0. Why is this so? Because I have proven here also how these things are 0. So I thought you might already read about these things. So I'm covering in this manner. So that's how the dot product can be written in this way. There is another form of writing this thing, which is I cap dot j cap is equal to del I j. This thing is called a direct delta function or Knocker's delta. It is 0 when I is not equal to j, and 1 when I is equal to j. So you can simply see when I dot I cap, it will be simply 1. When I dot j cap, it will simply be 0. Sorry, I dot j cap, it will simply be 0 because they are not equal. So that's how you can write the first property of the scalar product. Now moving on to the second property, which is nothing else but which I have defined earlier also. Now you can represent a vector in this form: ax I cap plus by j cap plus az k cap, and b vector you can also represent it in this manner: bx I cap plus by j cap plus bz k cap. Multiplication of these two can simply be written as ax bx plus ay by plus az. That is multiplying with the same components, together. If you multiply the same components together, it will result in this. Now let's move on to the third property, which is this: that if I multiply a vector dot with b vector, it will be simply same if I multiply b vector with the a vector, which is nothing else but the commutative. This property is called commutative. So as this property is called commutative, it means if I am going to multiply a vector dot with b vector, which is highly similar to multiplying b vector dot with b vector. So that's how the scalar product is done. Now let's talk about a few things more. First one is its physical significance or physical meaning. Now how the physical meaning of this quantity will be RT. You might already heard about the work done. Work done is a quantity which tells us how much work is done. Right? Simple as that. Work done is a quantity which tells us how much work is done. Now let's say there is some man who has to pull the cart into this direction. He has to pull the cart into this direction, but he is applying force in this direction. How much work he is doing or how much displacement will he cause can simply be told by simply taking the dot product of, which will tell us about the work. Why didn't I simply multiply with the force with the displacement? It's simply because we are not taking the force itself, we are taking the projection. That is how much force is acting in this direction. The force applied is something else, but how much force is acting in this direction will tell us how much work is done. How much force is applied in this direction will tell me how much work is done, rather than the force applied action. So that's how these are the physical meaning of the dot product. So these are some physical quantities in which we use dot product in order to evaluate such quantities like. So that's how the work done can be calculated. from here you can easily assess what is the physical meaning of the dot product. Now let's move on to an application part, which is projection. How to calculate projection of a vector. Now in order to calculate a projection of a vector, let's say you have two vectors here. First one is this A vector and second one is this B vector. You have to calculate the projection of the B vector up to the A vector. You can simply do it by multiplying the B vector with the unit vector along A. What is this unit vector? Now let me tell you. This is the projection of B. So unit vector is the vector divided by its magnitude. Vector and divided by its magnitude, it will simply result in the direction in which it is. So unit vector tells us about the direction of the particular vector only. It does not tell anything about the magnitude because the magnitude has been divided. So that's how it can be calculated. It is nothing else but the B cos theta. You can easily evaluate it. Right? If I just multiply A here, it is nothing else but our dot product law. So that's how it can be represented. Now let us evaluate about the cross product. And afterward we are going to do some questions related to the scalar and the dot product. These are all the things about the dot product or the scalar. Now the scalar product or the dot product is stated when your vector is a real vector. Now let me talk about this thing as well. This is the point number 5. It's called as a dot product when your vector is real. And it is called inner product when your vector is complex. When your vector is a complex quantity, it's called as an inner product. And you might think where the complex vectors are used, it is used in the quantum mechanics. You might already heard about the psi, in which we write the state of a system. Or we call it as a wave function as well. It is represented in the form of a complex vector. And the space formed by it is called as a complex vector space, which is eventually called as Hilbert space. So these are the physical significance of this dot product. We use the dot product in the case of the quantum mechanics as well. The core of the quantum mechanics is nothing else but your dot. So that's how we evaluate the dot product. So now let's talk about the cross product. And after we are going to talk about the representation of the cross product or vector product. Now it is usually represented in this manner. This is the cross product of A vector and B vector. It is usually represented in this manner and can also be written in this manner as well, as we have earlier written for A and B vector as well. It can also be written in this manner. And the resultant here is a vector whose unit vector is n, perpendicular to both. Perpendicular to both of them. The resultant here is a vector which is perpendicular to A vector and B. So resultant is basically perpendicular to A vector as well as B. That's how it is. Now these things are nothing else but the magnitude of A and B, and this shows the direction. This is the magnitude part and this is the direction. In the previous case there was no direction at all, there was only magnitude associated with the product. So this n cap is basically unit vector perpendicular to A vector and B. This unit vector is perpendicular to A vector as well as B. Now this A cross B vector is usually represented in this manner: I cap, J cap, K cap, AX, AY, AZ, BX, BY, and BZ. By solving this matrix, you will get the cross product of these two vectors. Let me solve for this. You don't have to remember this. I'm just telling you how to solve. Let's say for the I cap, I simply have to solve this co-matrix. So it will result me AY, EZ minus AZ, BY plus J cap. Some of you might already use negative here, but I'm going to take this first and this last. So that's how I'm going to use this as positive. So it will simply going to become AZ, BX minus AX, BZ plus K cap. It will become AX, BY minus BX. So that's how the cross product of these two can be evaluated. Now let's move further on. Now moving further on, now we are going to calculate in the similar manner for the theta is equals to 0 as well as theta equals to 90 as we have done for the previous case. Now let's say in this case A is basically parallel to B, and in this case A is perpendicular to B. These are two scenarios here. For this I am including even 180 as well. In the previous case I didn't include 180 because cos 180 is not 1, it is minus 1. Now in this case when I am going to take the product of A vector dot B vector is equals to magnitude of this into sin theta. So sin theta for theta equals to 0, sin theta 0, 180 and up to any multiple of 180 or even multiple of 90, let's say like this, or any multiple of 180, it will be simply 1. It will simply be 0. It will be simply 0. So the A vector cross with B vector is 0. So when the two vectors are parallel, their cross product is 0. Or we can call these kind of vectors as collinear vectors. When two vectors are moving in same line or headed in same line, these kind of two vectors are called collinear vectors. This is A vector A, this is vector B. As they are headed in same line, this means they are collinear vectors. So these kind of vectors are called collinear vectors. Now moving on, this one, when they are perpendicular to sin 90 degree is 1. Sin 90 degree is basically 1. So the A vector cross with B vector is equals to magnitude of A vector, magnitude of B vector, sin 90 n cap. It will simply going to result in A cap B sorry, a vector magnitude, b vector magnitude. That is, I'm multiplying this a vector with this b vector. Let's say this is a vector, this is b vector. The resultant will be simply another n cap if these are, and the magnitude will be simply a and b. Multiplication of the magnitude of a and b. Now you might already think that it might something look like the coordinate axis also. And we are going to use this particular property in order to define our property. Let's start the properties of cross product. Properties of the cross product. Now for the cross product, if I'm going to take I cap not with I cap, it will result in 0. That means I cap not with I cap will result in 0 because these two things are parallel. Similar manner, j cap cross with j cap will result in 0 because again it's again a parallel vector. Now I cap cross with j vector, j cap is equal to k. I cap cross with j cap is k. Or I can also say j cap cross with k cap is basically I cap, or k cap cross with I cap is equal to 0. Now we are multiplying here two perpendicular vectors and it will result in another vector which is perpendicular to both of them. That's how these three are related. Or you can also think in this manner, I cap, j cap, k cap. If you are multiplying these two, you are going to result this two. If you are going to multiply I and j and k, it will result into I. And you can remember in this way. I multiplied with j will result in k, k multiplied with I result in k. You can remember in this one. If you are going to take j with the I, it will result in k but in the minus. So j cap cross with I cap is not k cap, it's minus k. It's minus k, which leads me to my another property which is commutativeness of this particular scenario, which we will discuss in the second point. In similar manner, if I take k cap cross with j cap, it does not result in I cap, it will result in minus I cap. So let me define the vector properties of these quantities in such a manner that I cap cross with j cap is equal to epsilon I j k to k, where this epsilon is called Levitas-Levitas symbol. Where this epsilon is called Levitas-Levitas symbol, which is 1 if all the I, j and k are different and as well as cyclic. Different as well as cyclic. They are minus 1 if they are different and non-cyclic. It is minus 1 for these scenario in which it is non-cyclic, that's how it is minus 1. And 0 if two quantities of them are, as you can see from here, I cap dot I cap is 0. If they are same, I j or j k, if any of these quantities are same, then we can see it is this epsilon I j k is called Levi-Strauss. So that's how the cross product of the vectors is been defined. If you want to define for the two unit, that's how it is. Now, which leads me to my second property, which was nothing else but our commutativeness. This vector multiplication is not commutative. It is not commutative. If you are going to cross product A with B, it is not similar to cross product of B with A. It is not similar of the cross product of B. It is a minus of B vector, cross product of B vector. That's all. Now let's move on to the third property, which we are again going to take our definition of the very cross product, which is A vector is AX I cap, AY J cap plus AZ K cap, and B vector is nothing else but BX I cap plus BY J cap plus BZ K cap. Then our A cross B is simply defined as I cap, J cap, K cap, AX, AY, AZ, BX, BY, and BZ. That's how it can be defined. So this is our third property of the cross product. Now let's move on to the another property, which is physical meaning of the cross product. The physical meaning of the cross product is that it tells us the area swiped by the parallelogram, or it can be used in the scenario where we need to calculate the area swiped by the two vectors. Where we need to think about area swiped by the two vectors. Now let's take the similar example. A vector is in this direction and the B vector is in this direction. In the previous case, we used to take the projection of the B vector along with the A vector and try to take the product in this direction. But in this particular scenario, what we are going to do is we are going to multiply these two vectors as in such, and now going to see how much area is been swiped if they are the side of a parallelogram. They are side of the parallelogram. Now for that, what we have to do, the area of the parallelogram is, now let me represent area of parallelogram by this delta. I'm going to represent the area of the parallelogram by this symbol delta. The area of the parallelogram is simply side two parallel sides into distance between them. Sides and the distance between them. This is the distance between them. If this is the side, these are the two parallel sides, and I am going to multiply these parallel sides with the distance between them. It's going to simply result into the area. Okay? So it will simply going to result into the area. How to find the distance between them is simply taking the projection along the y direction. Previously we have took the projection of the B along the x direction. Now we are going to take the projection along the y direction, which is nothing else but B sin theta. So it will become A into B sin theta. Or I can write A vector magnitude, B vector magnitude into sin theta, which is nothing else but our cross product definition. Carry on definition. So that's how we can find the area of the parallelogram by multiplying two vectors. But for this parallelogram, it's not, the area is not a scalar quantity. The area here is a vector quantity which is pointing upward. The area here is a vector quantity which has a normal going in the upward direction, which is perpendicular to both A vector as well as the B vector. So here the resultant of this particular scenario is nothing else but a vector quantity which is pointing in the upward direction. So we have defined a plane, and the perpendicular to that plane will be a vector which is defined here as a vector quantity calculated from the previous two vectors. Now we have calculated area of the parallelogram. By using the same thing, we can calculate the area of a triangle as well. Now let's see how to calculate the area of the triangle using vector. Now let's see. Here's our first. This is the first. vector, this is our second vector, and let's say our third. Let's say this is A, this is B, this is C. Let's say this is point A, this is point B, and this is point C. These are the vector up to this point from origin. Let me not write these things as vector. Let me not write these things as vector. So you might get confused. So these sides are not vector, but these points are vector from the origin. So if I'm going to write this point, if I want to write this vector, I have to write it in this manner, B vector minus C. If I have to write this vector, it is either A vector minus B vector. And if I need to write this one, it is nothing else but the A vector, minus C vector. So that's how the sides of the triangle can be written. Now let me complete this triangle by simply drawing a line parallel to it and line parallel to it. Now as you can see, it again becomes a parallelogram. The area of the parallelogram we have earlier calculated comes out to be AB vector crossed with AC vector. This is the area of the parallelogram. I am using the same symbol for the area. Now multiplying it with the half will get me the result for the triangle. This is the entire area swiped. The half of this area will be the area of the parallelogram. Sorry, will be the area of the triangle. That's how the area of the triangle can be calculated. Now half B vector minus with A vector cross product with C vector minus C vector. So multiplying simply this side with this side, cross product. Taking the cross product of these, which is nothing else but the sine angle of this side multiplying with this side, which is nothing else but the same as the area of the triangle. Now multiplying this inside, I will get B vector cross with C vector minus B vector cross with A vector minus B vector. So I have already multiplied it. A vector cross with C vector minus A vector cross with A vector. This is plus vector. So it can be represented in this way. Now A vector dot A vector cross with A vector is simply going to be 0. Why this is 0? Because these two are parallel. A vector is parallel to itself. That's how the cross product of that particular vector with itself is going to be 0. So the area is half B cross with C. Now this is B cross with A with the minus sign. If I'm going to take the reverse of it, I can simply take the minus of it, which is A vector dot B vector plus sign with it plus C vector cross with B vector. That's how it can be written. So that's how it can be written. So this is the area of the triangle you need to calculate. So I have calculated area of triangle as well. We have calculated the area of. We have already calculated the area of the parallelogram. So that we have calculated till now about the multiplication of two vectors. Now let's talk about the multiplication of three vectors. We have talked about the multiplication of two vectors. Now we are going to talk about the multiplication of the three vectors. Now it is called triple product. Now there are two types of triple product as well. First one is scalar triple product, and second one is vector triple product. First one is scalar triple product and second one is a vector. Here we are going to multiply three vectors with each other. Let's say there is one vector A, another vector B, and another vector C. We are going to multiply them together and going to see the resultant. If the resultant comes out to be a scalar, and it's a scalar triple product. If the resultant comes out to be a vector, then it's a vector. Now let's define for these. First one is our scalar triple. First one is our scalar triple product. It is usually represented in this manner: A vector dot with B vector cross with. It is usually represented in this manner, and also represented in this manner: A, B, and C. This is the representation that you have to take the matrix multiplication. This is the representation of the matrix multiplication, and it is usually written in this manner: A1, A2, A3, B1, B2, B3, C1, C2, and C. This is the meaning of this multiplication. This is the meaning of this particular symbol. So that's how the scalar multiplication is done. The resultant to the scalar multiplication comes out to be is always a scalar quantity. As you can see, this is A dot with B cross C. Right? The B cross C will result in a vector quantity, and it's already a vector, and the dot product between them will result in a scalar quantity. Hence, the resultant of the vector, scalar triple product is a scalar quantity. Now, this is one way to represent scalar vector triple product. Another way to represent scalar triple product is B vector dot C vector cross with B vector. So I can write the same triple product in any of these three manners. I can write the same in any of these three manners. But the position is this thing that it should be moving in a cyclic manner. It should move in a cyclic manner. Now, then it basically states that if number of interchanging, that is I have interchanged A with B, B with C, C and D, and these kind of interchanging of row and column in a determinant is odd, then there will be a negative sign associated with it. If it is even, then it's simply going to be positive. If it is even, then it's simply going to be positive. If it is odd one, then it's simply going to be negative. That is, if I change AX, AY, AZ, CX, CY, CZ, BX, BY, BZ. Now in this scenario, you can see I have changed only one time, and it can represent it as A vector dot C vector cross with B vector, which is negative of A vector dot with C vector cross with B vector. If I would have changed it twice a time, that means I have changed the C with this as well, then it would have been represented by a Cx, Cy, Cz, Ax, Ay, Az, and Bx, Dy, Dz, which is equals to C vector dot with A vector dot B vector. So I have taken that transformation twice here, and it will be simply equal to A vector dot with B vector cross with C, which I have stated here as well. As you can see from here also. So that's how it can be represented. So if you are now going to take the transformation, if you are going to take even transformation, only then your product will be similar to the previous one. If you are going to take odd number of transitions, your product is not similar to the previous one. It will be simply different to the previous one. So that's how it can be. So these are the few even properties I have mentioned in between also. Now let me talk about another thing as well. Now what is the physical meaning behind this scalar triple product? Now in the previous case, when we are using cross product, we used to calculate the area of the parallelogram. This is used to calculate the volume of the paraboloid. And can be represented in this. I'm taking the mod here because I'm representing it by scalar. Because the volume is a scalar quantity, right? Volume is a scalar quantity, so I'm writing this mod. Or you can say the volume of the box. Now let's say this is our A vector here. Let's say this is B vector here, and this is our C vector. We have to calculate this, the volume of this box. Volume of this box. So the volume of this box can be represented in this A dot with B cross with C. With the B cross C, you are going to calculate what is the area swiped, right? The B cross C, you are going to calculate the area swiped, right? And this is the height of the box. When you are multiplying this area swiped with the height, it will get you to the volume of the box. So it will get you to the volume of the box. I can also write it in this manner: A vector mod B vector cross C vector mod into cos of. Now this cos of theta is basically the angle between this normal of the B cross C and E. Now let me draw this diagram. This is B and this is C, and here goes the normal of this. And if A is directed in this direction, then the area between normal theta is angle between A vector and N. But the theta I have defined previously, this cos theta, this theta defines the angle between N cap and the A vector. That's how the triple product have been defined. Or I can simply say now this A cos theta in this magnitude term is nothing else but the height. And this B cross C is the area. This B cross C is the area part. Let me write in the magnitude sense again. This is the area and this is height. Again, simply multiplying the height with the area, I am going to get what? The volume of the paraboloid. Now it is also used, as we have used earlier, the vector product, the cross product of the vectors to calculate if the two vectors are collinear or not. This is also used to calculate if the two vectors are coplanar or not. Vectors are coplanar. So if vectors are coplanar, that means A vector here and the B vector is again in the same plane and the C vector is again in the same plane. All of these are in the same plane. Then in that case, there will not be any volume occupied with this paraboloid. So I can simply state this thing: A vector dot with B cross C vector is equals to 0. So that there won't be any volume occupied with it, and hence it can be represented as A vector, or the scalar triple product of these three is simply going to be 0. If the vectors are coplanar, that means if all the vectors lie in the same plane, then their scalar triple product is simply going to be 0. That's how it can be. These are the few things that we used to know about the scalar triple product. So a few things more: if your vector Ax, Bx, Ay, Az, Bx, By, and Bz, and Cx, Cy, and Cz comes out to be 0 or not equal to 0. There are two similar scenarios in which this comes out to be 0. Then your vectors are said to be linear dependent. If not equals to 0, then they are called vector linear independent. If not equals to 0, then they are called linearly independent. Now, if all vectors are linearly independent, A vector, B vector, and C vector are linearly independent. I'm going to write in this manner: linearly independent. Li means linearly independent. Then I can write another vector D in the form of addition of these three vectors with some constant. They can be used to make another set of vectors. If these are linearly independent vectors, then they can be used to make another set of vectors. If these are linearly independent, LD means linearly independent, then one of them vector can be represented as the addition of the two other vectors, and one of the vector can be represented as the addition of two other vectors. So that's how it can be. So that's how the vector scalar triple product is. This is all the information that you need to know about the scalar triple product. Now let's move on to the vector triple product as well. Vector triple product. After this, we are going to do some questions related to it after classifying the vector. So the vector triple product can be represented in this manner: A cross with B cross with C, or it can also be written in this manner: back minus cal. We can remember this in this sense also: back minus cal. Now here you can look, it is a vector quantity, and it is also a vector quantity. If you are going to multiply or take the cross product of it, the resultant should be resultant should be a vector. So the resultant should be a vector quantity. That's how it is been. So the resultant here is a vector quantity by multiplying three vectors consecutively together. That's how this is. Now in this particular scenario, what is happening here is a vector is multiplied with some m vector, which will result into something. But as we already know from the cross product part, that our resultant will be perpendicular to these two vectors. So the resultant, which is a vector quantity, resultant a vector cross with b cross c vector. Let me say this is r vector. This r vector is then going to be perpendicular to a vector. It is not going to be perpendicular to b or c vector. It is going to be perpendicular to a vector. If I represent it by a c vector cross with b vector cross with a vector, then it's going to be r vector is going to be perpendicular to c. So that's how the triple product can be. This is all there to know about the vector triple product. There is no physical significance associated with it. There is no another set of properties associated with it. There is only this much formula that you need to remember. Now let's talk about the four product as well. Now if you are going to multiply four vectors together, there are just only formulas associated with it. Scalar product is a vector cross with b vector dot with c vector cross with b vector. It is simply a vector dot c vector into b vector dot with b vector minus a vector dot with b vector minus b vector. Now how do you remember this? Let me tell you this. Make a matrix, write a vector here, b vector here, and c vector here, and d vector. Simply multiply a vector dot with c vector, a vector dot with b vector, and a vector, sorry, c vector, sorry, b vector dot with c vector, and b vector dot with b vector. And simply take the determinant of this quantity, you are going to get. That is the way to calculate the scalar product of the four. Scalar product of the four. Now moving forward, what is the vector product of the four vectors? So the vector product of four vectors is simply a vector, b vector, c vector. You might already recall this. This is nothing else but our matrix representation. With c vector minus b vector, b vector, c vector. So that's how it can be. So this is the vector product of the four. It does not even represent anything. It does not have any physical significance. I'm not writing anything. Now let us start doing some questions related to it. Questions which are really important as per your exam. Now let me start with the very first question. Sorry, before that, let me write the types of vectors as I told you. There are types of vectors. We will continue with the types as I have defined two types within while defining the product of the vector. Those two types were coplanar vectors and another one was the collinear. I'm not going to define them again. The vectors I'm going to define here is equal vector. Now two vectors are said to be equal. Let's say A and B are two vectors, are said to be equal if they have same magnitude as well as the direction. If they have same magnitude as well as direction, then they are called to be equal vectors. They are represented in same direction and have the same magnitude. So their length is also same. Next one is opposite vectors. Opposite vector is nothing else but the reverse of equal vector. They have same magnitude but opposite direction. So A vector is in this direction, B vector is in this direction, and the A vector is simply the minus times of B vector. This is your opposite vector. The next vector is unit vector. Now the unit vectors are those vectors whose magnitude is 1 or who simply represent the direction. Represent directions of it. Because their magnitude is unity. Their magnitude is unity, they only represent direction. For example, I cap, j cap, and k cap, these things are nothing else but your unit vector. The next vector is called cyclic vector. Cyclic vector is that vector whose head and tail lie at the same point. Head and tail lie at the same point. For example, this kind of vector, whose head as well as tail lie at the same point. These kind of vectors are called cyclic vectors. So these are the few types of the vectors that I have explained. So now let's start with the question part. Let's practice the question now. Now let's say if A vector plus B vector plus C vector is equal to 0, then find angle between B vector and C vector. You have to find the angle between B vector and C vector. You have been given with the data that A vector plus B vector plus C vector equals to 0. How can you find the angle between B and C vector? So this is your question. How should we do it? This is written in this form. Let me write A vector is equal to minus of B vector plus C vector. I can write in this manner, right? I can simply write in this manner. Now let me take the dot product of A with itself. A vector dot product with itself will simply give me, here it will give me dot product with, so simply taking the dot product with this. Now multiplying this two will become A square as I am taking the A vector dot with A vector, which is nothing else but the magnitude of A vector into magnitude of A vector into cos of theta. The cos of theta here is 0, which is 1. Cos 0 is basically equal to 1, which is nothing else but A square. So it will become A square. Hence minus and minus sign put together. It will also become B vector dot with B vector plus B vector dot with C vector plus C vector dot with B vector plus C vector dot with C vector. Now it simply becomes b square plus c square plus twice the time of c into b into cos of theta. I have simply added these two terms and taken cos theta. Yep. Now this I'm taking this these things from this side to other side. It will become a square minus b square minus c square is equal to 2cb cos of or cos theta simply becomes a square minus b square minus c square divided by 2c. That's how you can calculate the angle between b and c. Now let's do some more example over it. Now write down coordinates of corner of cube of unit side origin at one point. Let's say there is some cube. There is some cube. There's a cube like this. Let me name it like A, B, C, D, and then E, and F, then G, and then let me name it like this. You have to name all the vectors here, all the points. Now this point is nothing else, but it is along y-axis, it is along x-axis, and it is along z-axis. So this point is 0, 0, 1. This point is 0, 1, 0, and this point is 1, 0. Similarly, you have to name all these. This point will simply going to become 0, 1, 1. One unit along the y-axis and one unit along the z-axis. So it's going to become 0, 1. It's going to become 1, 1, 0, and it's going to become 1, 0. This one is going to become 1, 1. Now this is the first part of the question. The second part of the question is find angle between face diagonal of cube. Find the angle between the face diagonal of the cube. How should we find the angle between the face diagonal? Face diagonal is basically the diagonal along the face. Let's say my first diagonal is this thing and the second diagonal is this. So basically I have to find the angle between AG vector and AC. How can I find the angle between these? Now in order to calculate the AG vector, I simply need to subtract this point from this point. For AG this point to this point and for AC this point to this point. Subtracting it, it will simply going to result in I cap plus 0 j cap and k. So the vector AG vector simply becomes I cap plus k cap. And the AC vector simply becomes j cap plus k cap. So this simply becomes j cap plus k cap. Now one becomes I cap plus k cap, another way one becomes j cap plus k cap. In order to find the angle between these two, I'm simply going to take the dot product of the two points. Now AG vector dot AC vector, which is equal to 1 because these two are perpendicular. So is equal to AG vector dot AC. Now I have to calculate the magnitude of these two. Magnitude of AG vector is 1 square plus 1 square is equal to 2 under root 2, and similarly goes for the AC vector as well, which is again 1 square plus 1 square is again equal to under root 2. Now how I have taken 1, I have told you, let me show it like this, that the AG vector is nothing else but equal to AC vector. But in magnitude these two things are equal. So if instead of taking the dot product of AG to AC, if I take the dot product of AC to AC, will it result me the same thing or will it result me the different thing? Will it result me the same thing or will it result me the different thing? It will simply result me the same thing. That's how I consider them parallel here, and I've taken it equal to. So it is equal to under root 2 and it is also equal to under root 2 and cos theta. So, or I can prove this as well. AG vector dot AC vector. AG can be represented as I cap plus k cap, and it can be also represented as j cap plus k cap. There is no coefficient of j in this, there is no coefficient of I in this. So I'm going to take the product here, only k cap dot with k cap, which is nothing else but. So that's how it can be. It will become simply equals to 2 cos theta, and the cos theta will simply become 1 by 2. So theta comes out to cos theta is equal to 1 by 2 and theta equals to 60 degree. Hence we have calculated the angle between the faces. Now the third part of this question. Third part of the question is find angle between body diagonals. Now what is body diagonals? Body diagonals is similarly as that of the face diagonal, but it is within the body. It is again a diagonal quantity. Now these are the diagonals from A to here H, and the another one is B to E. So now we have to find the angle between A to H and B to C. AH vector and BE vector. Now AH vector can simply be written as A cap, J cap plus K cap. Now the BE vector can be simply written as subtracting these two. So simply subtracting E from this part. So what I'm going to get is I cap plus J cap minus K cap. So simply taking the dot product of these two quantities, AH vector dot with B dot vector, taking dot product of these two quantities, it will simply become 1 plus 1 minus 1, again result me into 1. Now we have to take the magnitude of this thing. Now the magnitude of this thing simply 1 square plus 1 square plus 1 square, taking the under root of it, it will simply become under root 3. And the similar goes for the BE vector as well. So let me write the entire condition here, which was AH vector dot with BE vector, which is equal to AH vector magnitude, BE vector magnitude, cos of theta. This comes out to be 1, this comes out to be root 3, this also comes out to be root 3, this is nothing else but cos. So cos theta comes out to be 1 by 3, or you can write theta comes out to be cos inverse 1 by 3. So these are some examples related to the dot product of your dot product that we have explained in this. We will do some more examples in the next upcoming class. So this is it for now, guys. Thank you guys and happy. Hello learners, this is Nikhil Mayer. Welcome to IIT. So today we guys are going to start our new topic, which is mathematics. We are going to be starting with the vectors, and we are going to continue with more and more topics thereafter. So we are today going to start with the vectors. We will cover the vectors in the next 2-3 lectures, and afterwards we are going to talk about some different things. Today we guys are going to start with the vectors part. Now let's start with the vectors. Starting on with the vector. Now let us first define what is a vector. Before defining a vector, we need to define what is a quantity. A quantity can be divided into two methods. First one is scalar and another one is vector. So basically a quantity can be defined as a vector and as a scalar. The quantity can be defined